All right. Great. Well, we are on air and we're ready to do part 2 of synthesis for operator for the purpose of creating dubstep. So a couple days ago, it was the first time I was attempting a live streaming session like this, and I had a few technical difficulties. So I think I've got them all sorted out now, and so this session should be a little bit more informative. So just to begin, I'm going to do a bit of a recap on everything that I attempted to teach you during the last lecture. And this will be a really good review for me, and basically it'll give you a better idea of how you can visualize what sound is doing when it's traveling through air in real life. So then when we get into our program and we start using operator, we can really have a more of an understanding of what exactly we're doing with the sound wave to make our synthesizer create these sounds via our speakers. So I'm just going to pull up my worksheet from my website. If you want to follow along, I highly recommend doing so. All of my lesson information is on my website, so learnableton.spacefood.ca. Of course, you already know that because if you're watching this, now that I've got it fixed, you'll be able to access that just straight from my site. Just open it up in another window and pull it up. It's Synthesis and Dubstep Essentials, Part 1 of 2. And actually, I'm just going to mound all of the information that I have already put together for this lesson into this blog post. So where am I here? Is this it? There we go. Okay, so I'm just going to do my screen share. All right. So we're talking about synthesis. We're going to get to creating dubstep sounds, hopefully by the end of this lesson. And so I'll just hurry along. So the first thing we need to know is, what is sound exactly? Sound is energy. Energy travels through a medium. It's basically, well, it's kinetic energy. So just like when you create ripples in a pond, the energy that you're putting into the momentum of your hand or the rock or whatever is hitting the surface of the water, it has to go somewhere. Energy is never removed, it's just changed. So sound, for example, in this case, for example, when we're producing a sound, let's say with a guitar string, if I pluck the guitar string, the string is going to vibrate, and that vibration is going to cause a disturbance in the medium that's surrounding the guitar string. So in this case, unless you're playing your guitar underwater, the guitar string will be surrounded by air. So when you hear a guitar sound, it's you're not actually experiencing the air that is surrounding the guitar string in your ear. What's happening is the guitar string is creating kind of a chain reaction, I guess. So the molecules in the air surrounding the guitar string that are initially being vibrated are bumping into one another and then forming a ripple or a wave. And that wave travels in a straight line into your ear. And basically, those ripples are concentrated by the pinna, or the outer part of your ear, into your ear canal. And your ear canal actually ends up amplifying a certain range of frequencies around the 2500 hertz area. And just so that you have a bit of a reference, the 2000 hertz to, maybe like 2800 hertz, that's where a lot of our consonants and sibilants comes from. So like t, t, k, k, t, 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 which is very interesting to know, because when we're talking, those sorts of sounds are really what allow us to understand the words that someone is saying. And you'll find when you start getting older, that's the area of frequencies that are probably going to start becoming duller faster, because they're just a very commonly used band of frequencies that your ear interprets. So anyway, the guitar string vibrates the air ripples and creates a waveform. The wave of air is focused by your pinna into your ear canal. The wave is then going to impact your eardrum. The eardrum is attached to 3 tiny little bones that are then attached to your cochlea. And your cochlea looks like a little seashell or something. It's like a spiral organ. And inside of that organ are tiny little hairs that end up vibrating to different frequencies within our hearing spectrum. And then those vibrations are then converted into electrical impulses that are then interpreted by your brain. So one thing that you should know is the human ear is able to hear between 20 hertz and 20,000 hertz, around there. There are people who are able to hear slightly higher than 20 hertz. I have heard before that females are able to hear slightly higher frequencies than men are, just based on maybe the size of their cochlea, or just maybe the size of their organs in general. So the definition of sound is mechanical vibrations transmitted through an elastic medium traveling in air at a speed of approximately 1,130 feet per second at sea level. So of course, pressure differences will impact the speed at which the sound is traveling, because it is a vibration. So if there's a higher pressure, those air molecules are going to be closer together, and then the sound will actually travel faster because of that denseness. So sound will actually travel faster through a denser material. So if you're sending sound through water, for example, the sound will travel faster than through air. But our ears aren't capable of hearing much underwater. Our ears are designed to hear sound through air. So if you get a chance, I highly recommend looking at this really excellent video. It's a cymatic video. It's just basically visualizing sound in a very interesting way. So we know that sound travels in waves. Now, the length of a wave determines how low or high the frequency is. So the higher the frequency means the more cycles are going to happen in that frequency band. So if we look at this picture here, I mean, there are a lot of terms here just describing the different parts of a wave, but we can see that the blue line will cross through this center point here. And this center point represents rest, or just the midpoint. So basically, if we're talking about a speaker, this line will be where the speaker is not moving at all. At this point, at the crest of the wave, your speaker will be pushed all the way out, and down at the trough, your speaker will be pulled all the way back. So of course, this blue wave, the taller it gets, the higher the amplitude. And if we see more of these crossing points through this midpoint during a certain length of time, that's going to be determining the wavelength. So 20 hertz is basically 20 cycles per second. And that's what hertz is. Kilohertz is hertz, but just times 2 decimal points, I believe. All right. of course, we measure sound waves in a chart representing volume or amplitude over frequency. So frequency would be the x-axis, and amplitude would be the y-axis. So let's move on. I don't want to get too caught up because I do want to get to operator here. Blah, 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 blah. Okay, so there are a few definitions that you should understand, so then you won't get confused if you're shop talking with some audio nerds. So cycle is a single unit of vibration. So if we look back at our chart here, one cycle is the 0 point. Crossing through the first time is half of a cycle. And then when it makes it back to its 0 point, then you'll have a full cycle. A good way to think of it is basically a cycle is sound's circle. It essentially is just creating a circle, but because we have the time variable, it gets mapped out into a wave shape like this. But essentially, it's a circle or cycle. Frequency is indicating, or frequency means the speed of vibration. So high frequency is many cycles per second, and a low frequency is fewer cycles per second. So in return, high frequency would be a high pitch, low frequency would be a low pitch. Hertz, of course, is what we use to describe how or what the frequency is. So cycles per second. Kilohertz equals 1,000 hertz. So it was 3 decimal points. The audible frequency range for humans, of course, 20 hertz to 20,000 hertz. So when we're talking about sound, there are 3 elements that we have to be aware of. These 3 elements really determine how a sound can be differentiated by differentiated from other sounds. So the first element of sound is a sound's pitch. So pitch is the musical term for frequency. For example, if we're looking at a pitch of 440 hertz, that actually equals A. So the musical note A. So timbre is referring to a tone's harmonic structure. Timbre can be described basically as the harmonic frequencies that help us differentiate a tone from another tone. And I'm going to demonstrate that using Ableton Live and Operator. So let me just shrink this down. Okay, so right here you can see that I've got my Ableton session set up, and I have an instance of Operator. So Operator, I'll go over all the areas of Operator and what it does, but essentially it's a synthesizer that allows us to use 3 types of synthesis. We can use FM synthesis, or frequency modulation. We can use additive synthesis, or we can use subtractive synthesis. Operator also gives us a lot of really excellent options for adjusting the volume envelope, filter envelope, or we can use a low frequency oscillator to modulate any other characteristic of the synthesizer. So I'm going to just add an audio effect here by dragging it in. I'm going to use the spectrum tool, and basically the spectrum tool will allow me to visualize the frequencies that are being produced by the operator. Just as a review, the signal flow from any instrument down in the device view, which is this bottom part, travels from left to right. So I've got my instrument on the farthest point left, and so the sound is the MIDI data from my keyboard is going to travel into my operator from the left, and then the sound that the operator is producing is going to leave the device from the right, and I'll be able to see the volume on the right here as it's produced, and that volume will enter the spectrum device and then exit the spectrum device without altering without altering the signal unless I've made some sort of adjustment to whatever device. Okay, so 440 hertz tone should be here. Oh, no. Here we go. So this is a 440 hertz tone produced with a sine wave. And so a sine wave is the basic building block of every other type of waveform. You might be familiar with the other waveforms, including the triangle wave, the saw wave or ramp wave, the square wave, or pulse wave. And basically, all of those other waveforms are made up of sine waves. The waveform is just dependent on how many harmonics there are and which harmonics are present. So a sine wave can be referred to as a pure tone because it is only the fundamental frequency, so the main lowest frequency, without any overtones or harmonics on either side of the tone. So you can see when I'm playing this, I mean, there are some slight overtones being generated. It might just be from the program, but there are no other frequencies on either side of that tone. So if I want to create a square wave, I can go to this display area and just show you what a square wave looks like. Actually, let's show you a saw wave first. Here we go. So you can see down in this area that we're presented with a bit of a ramp. And that's just indicating the saw wave and its harmonics. So if I play that same 440 hertz tone, you'll be able to see the harmonics of this saw wave. And a saw wave contains all harmonics, even and odd, but at gradually reduced volumes. So you can see that there was the fundamental frequency, and all of these frequencies above it are called overtones, partials, or harmonics. And those tones are what affect a sound's timbre. So it's this harmonic content that allows us to differentiate between my voice singing an A note or a trumpet playing an A note. So there's a lot of power in those overtones. You can basically construct any tone using a combination of harmonic adjustment and volume and filter envelope automation. And we'll get to that a little bit later on. Okay, so let me just pull this back up here. The very last element of sound is volume. And as I mentioned before, the volume envelope is what will let us start mimicking some of the parameters or characteristics of a real-life tone. So, for example, if I'm to play a note on a violin, the violin sound is going to have a very slow attack. So it's going to take a short amount of time before the note that I'm bowing is going to reach its maximum volume. Whereas if I'm playing something like maybe a steel drum, or if I'm playing maybe a triangle, that sort of tone is going to have a very sharp attack, and depending on what the instrument is, it's going to have a very quick decay, a very short sustain, and a very fast release. So if you aren't familiar with envelopes, I'll just cover this really quick. In the operator, you can see that we have two different views. Right now, we're looking at the oscillator view, which presents us with all of our harmonics. But if we click here, then we'll be presented with the volume envelope. And the volume envelope allows us to adjust the attack, decay, sustain, and release of our note. So if I'm to create something that sounds a little bit closer to a violin, I'm going to adjust the attack so that it's slightly slower than immediate, like this. You'll see it's ramping up. And then maybe I'll let it decay slightly. And when I let go of the note, I do want it to decay slowly, but I don't want it to, I don't want the tone to be held on for too long before it completely creates silence. The saw wave might not be the best tone for this, but let's listen to that envelope. I'm not sure if you can hear that. I'll just turn it up. And I'll adjust the attack so that it's slightly slower. So you can hear that once it's reached its maximum value for its attack, it quickly drops in volume, and it's held there until I let my finger off of the note, and then it does quickly dissipate into silence. So let me adjust the decay. I'm going to reduce the decay a little bit. Oh yeah, sorry, I adjusted the release. So when I let go of it, the note will hold on for slightly longer. And let's test this out. So an envelope is essentially just a built-in type of automation. It's just a type of automation that is essential to creating synthesized tones. Now, ADSR is just the basic method of an envelope. There are a bunch of different types of envelopes, but you can pretty much accomplish most sounds using this basic ADSR method. Let me just see here. Okay. Let me just pull up my notes here again. Okay, so now that we understand the three elements of sound, we can start looking into the components of a synthesizer. Now, these components of a synthesizer are going to be the same for any synthesizer that you play with, whether it's super old or it's really, really new and advanced. They might just rename some of these components to sound, I don't know, hip or something, but you should be aware of these because these are going to be the components that you're going to be manipulating in order to create the tones that you want. So an oscillator controls pitch. The oscillator is going to be generating an oscillating electric current or voltage by non-mechanical means. So we know that sound is an oscillation in a medium such as air. So with an oscillator, when we're referring to a synthesizer, we're talking about an oscillation of electricity. That's basically what an oscillator does. We're creating a waveform in electricity. An amplifier is an electronic device for increasing the amplitude of electrical signals used chiefly in sound reproduction. So the amplifier is what's going to allow us to automate or create a volume envelope to mimic sounds like snare drums and string sounds. Filters, there are many different types of filters. Some of the most common types of filters are high pass, low pass, notch, band pass, and shelf filters. So filters either increase or decrease the upper or lower harmonics. An audio filter is frequency-dependent amplifier circuit working in the audio frequency range from 0 Hertz to beyond 20 kilohertz. So filters are very important in synthesis because they allow us to mimic some of the natural filtration that happens when we're playing an instrument or even when we're speaking with our mouths. So one example I used on Monday was speaking with my mouth. So when I'm talking and moving my lips, opening and closing my mouth, it's actually a form of subtractive synthesis because my lips are acting as a type of filter, removing the harmonics as I close my mouth. And as I shape my mouth, I'm actually resonating frequency bands differently, so then I can start creating like ow, ooh, ee sounds, which we can understand as words. So if you can visualize a filter basically blocking out harmonics, you're on your way to knowing everything about filters. So a filter envelope is exactly like a volume envelope, except for it's controlling any type of filter that you've got connected to it. So then you can adjust how quickly a filter's cutoff is opening or closing based on that familiar attack, decay, sustain, and release chart. We talked about the volume envelope. The pitch envelope, of course, is the same, except for it's going to be connected to the automation of an oscillator. So a good example of using a pitch envelope for synthesizing an organic sound is using a pitch envelope for a bass guitar sound. Because when you're pulling a string tight on any type of stringed instrument, you're tightening the string to a point where it's actually going to be producing a higher pitched tone at first, and then dropping into its fundamental frequency after you've let go of it. But it's only very slight. It's hard to pick up, but it does make a very big difference. So if you're trying to synthesize a bass tone or guitar tone, your attack of that pitch should, or attack of that tone should definitely be slightly and quickly pitch shifted from like a higher tone down to your intended frequency. Now, low frequency oscillator is going to be a really important one for you to know for a lot of reasons, but in our case, when we're talking about creating dubstep sounds, low frequency oscillator is integral to how we can get that rhythmic wobble sound. So a low frequency oscillator is exactly like a regular oscillator, except for it oscillates at a signal that's usually below 20 hertz. And with our Ableton's operator, we're able to attach the low frequency oscillator's rate to the tempo of our session. So we can have it open and close some sort of parameter at a 16th note, quarter note, 32nd note, etc. And so that's really useful for creating that wah 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 sound that we're going to be experimenting with very soon. So of course, we've talked about a sine wave, pure vibrations. All frequencies are made up of sine waves. Square waves are kind of an interesting wave because they have only odd harmonics. And when we use a square wave for a low frequency oscillator, it creates a very abrupt opening and closing sound. Kind of like if you listen to a siren or something going, it produces that effect. A pulse wave is just like a square wave, except for we're adjusting the width of each half cycle. If you can imagine what I'm saying. I'll try to demonstrate that, but that's essentially what it is. So for a square wave, if we've got 50% on and 50% off, a pulse wave can be varied. For example, 30% on and 70% off. And you'll notice a really noticeable change in the thickness and the depth of the sound as you adjust that pulse width. A sawtooth wave or ramp can come in a ramp up or ramp down wave. It contains all harmonics, even and odd, and each of the harmonics are reduced by half of the previous harmonic's volume. So if the fundamental frequency was at 10 decibels, then the first harmonic would be half of that volume, so 5 decibels. All right, so a triangle wave is kind of a combination between like a square wave, a sawtooth wave and a sine wave, where the wave is gradually turning on for half a cycle, or for a quarter cycle, and then basically just creating like a triangle shape. It's got a very warm tone, I guess. Noise, we're referring to white noise here, and white noise is all frequencies being played at once at the same volume or the same amplitude. This is really good for creating percussive noises or just adding a degree of randomness. Okay, so finally let's talk about Ableton's operator a little bit, so then you can become familiar with how to use it in your own productions, especially for creating dubstep. So when you look at the operator's interface, you'll notice that there are 9 areas. Now the operator's interface is slightly different from most of the other instruments that Ableton Live has, in that this has a changing display window. Most of Ableton's instruments present every control right up front without having to open another window, except for like Sampler, where you have a few different key range editors. So the center of this instrument is called the display, and the display shows you all of the pertinent information regarding the oscillators that you're adjusting, or the LFOs, or frequency, or the filters, or the global section. So starting from the bottom left and moving clockwise, we have oscillator A at the bottom left. The coarse knob here has... Actually, let's move around the circle first. So oscillator A is bottom left, oscillator B, oscillator C, oscillator D. If we move over to the right side of this shell, is what this is called, we find the LFO section, so the low frequency oscillator, which is currently deactivated, the filter section, which is active and also gives us options for our filter envelope in the display. Here is the pitch envelope, which is deactivated. And also in the display, we have all of our options for our pitch envelope. And then finally, down at the bottom right, this is our global section. So the global section contains controls that will affect everything in this instrument. Okay, so back to the first oscillator. We've got our coarse knob here, which jumps up in octaves, I believe. And then the fine knob moves up in every 2 cent. Separation fractions, whole numbers, creating an inharmonic relationship. Okay, so it just jumps up in cents, I believe. Fixed. Okay, so with this button not turned on, so this is the fixed button. I'll try to explain this. I'm pretty sure I know it, but only half take my word for it. So with the fixed button off, the coarse knob is applied as an addition to the fine knob to create inharmonic changes in the oscillator's pitch. If we have fixed applied, then we have a frequency that's multiplied by the multiple knob here. So if we have 100 hertz and a multiple of 1, we will be presented with a 100 hertz tone. If we increase the multiple knob by 10, we'll have a 1000 hertz tone being produced. So all of these controls remain the same for each of these 4 oscillators that we've got. So Operator has 5 oscillators, and I think it's even got 1 extra oscillator that's hidden. So we've got the 4 main oscillators and the low frequency oscillator. I want to draw your attention to these colored squares here. I've heard them being called chiclets. And these chiclets are what indicate the algorithm that that Operator is using to create frequency modulation. So down in the global section, you'll also see a representation of these chiclets in a line. And when you select on this algorithm section, you'll find in the display that there are a bunch of different variations of this algorithm. So to describe the first one, the very bottom oscillator, which is oscillator A, is going to be creating the tone that we will hear. Now that's indicated by this yellow box that has a line coming out of it. So that line is just indicating that it's going to the output that's on the right of the Operator synthesizer. Now oscillator B, as we can see in the algorithm section, is connected to oscillator A. So if I'm creating a tone with oscillator A, the B oscillator will modulate the pitch of oscillator A. So if I create a very slow oscillation with my oscillator B, so let's say 10 hertz, actually let's make it even less, and I'm going to switch this to sine wave. Oh, I'm also going to adjust the filter envelope so that I have a quicker attack. And make note of how I'm adjusting this so then you can play around on your Operator at home. Okay, so we've got our tone here. I'm going to start turning up the amplitude of my B oscillator, which is going to modulate the A oscillator. And you'll be able to see a change in the spectrum. There we go. So that's a very, very slow frequency modulation. And so as we increase the rate at which the B oscillator is modulating the A oscillator, it's going to start creating interesting overtones, which will really allow us to start creating some interesting synthesizer sounds. So let's play around with that. So you can see there, it's almost creating like a square wave. Very interesting. So if A oscillator is creating the pitch that we're hearing, and B is attaching to A to modulate the pitch of the oscillator, then we should be able to deduce that the C oscillator will affect the pitch of the B oscillator, which will then affect the pitch of the sound that we hear. So let's test that out. And I promise you can get really nice sounds out of this synthesizer. You just have to mess around with it. Okay, so just like the C affected B and B affects A and A produces the tone, the D oscillator in this algorithm here is going to affect the pitch of the C oscillator, that affects B oscillator, that etc. and so forth. So we can adjust the algorithm by just clicking on any one of these algorithm choices here. So if we choose the algorithm that's on the far right, where all of the chiclets are horizontally placed, you can notice that those little lines coming out of the box are indicating that each one are going to be coming out of our output parallel, in a parallel sequence. So the D, C, B, and A oscillator will not be having a frequency modulating effect on each other. Instead, they'll all be producing tones that will come out of the output of our operator. So some of these other ones here, so like for example, this square one, we're basically going to be hearing two oscillators producing sound. We'll have the A oscillator producing sound. We'll have the C oscillator producing sound. And the B and D oscillators will be modulating the A and C oscillators. So I encourage you to go through all of these and just experiment with how each one of them can change your sound quite drastically. Okay, so moving on to the LFO section. First, I'm going to... Okay. Okay, so the low frequency oscillator, as we know, is going to be modulating whatever parameter we set here. In this case, the low frequency oscillator is sent to either, in our display we can see it's sent to either destination A, B, C, or D, or all of them, or we can send it straight to the filter section, which will create our dubstep wobble. So let's test this out. Right now we've got LFO activated. We can see by the orange LED being illuminated. We have the sine wave selected currently, and I'm going to reduce the rate so that we can hear this more pronounced. And actually, I'm going to create a... I'm going to use a waveform that has a few more harmonics than a sine wave, because we know that sine waves are pure tones, and so I just want to get something that has a bit more grind. So square wave with 64 harmonics. Okay, so you can see all of those harmonics there. So the rate, of course, affects the rate at which, or the frequency that the LFO is oscillating. The amount just affects the depth at which the LFO, or I guess the amplitude of the low frequency oscillator. So right now I've got rate selected, and rate will just give me just an arbitrary number. I can select any number between 0 and 127, but if I select the R, I'll be able to switch from... Oh yeah, okay, so R is just indicating re-trigger. So if I've got R selected, then the oscillator will re-trigger at its 0 point. But if I don't have the R selected, it will continue oscillating at the same spot that I had originally left it. So, all right, so let's listen to the difference between these different waveforms in our low frequency oscillator. So the square wave sounds like that. Triangle. That's sounding pretty dubsteppy. So that's obviously a saw wave with an up ramp. Down ramp, and we'll these are basically random. Okay. So in our LFO, we can adjust all of the parameters that affect the LFO in the display window. So we can select its destination. We can also select how much it's affecting its destination. So whether it's affecting the oscillators from A to D, or the filter, or it can even affect all of them, which creates another really interesting effect. We can also create a secondary destination. So we can attach the low frequency oscillator to any of these other parameters. So then we can use that modulation in some sort of rhythmic fashion, or just to create a tone that's more complex and interesting to listen to. And then, of course, on our display, these are all of your envelope options that you can use. Down in the filter section, we're given the option to choose any one of these 5 types of filters. We have a low pass filter, high pass filter, we've got a band pass filter, a notch filter, and then this is, I think this is a high or low pass filter with, I actually don't know what that is. I will get back to you on that filter type. Interesting. Okay, so the 12 and 24 is just indicating how steep of a cutoff the filter is going to have. So when we have 12 selected, it's going to be attenuating the tone at the cutoff point by 12 decibels per frequency. Per octave. At 24, it's going to attenuate the frequencies at the cutoff point by 24 decibels per octave. The frequency is indicating where our cutoff point is. The resonance is going to impact if there's going to be a bit of emphasis at the cutoff point, which can be really useful if you're creating some like more mouthy sounds, or if you just really want to emphasize the edge of that filter cutoff. And of course, all of these parameters can be automated or modulated using the LFO. So down in the pitch envelope section, we can activate the pitch envelope by selecting the chiclet to the left. And we've got 3 controls. We have the pitch envelope amount, which will allow us to choose how deep or how much of an effect the pitch envelope is going to have on our tone. So let's just make this less annoying sounding. Okay. So I'll just demonstrate what I had been talking about regarding the bass tone. And I'm going to create a very quick attack, just a very sharp release in the pitch envelope. It's probably pretty painful to hear, but you can hear how the pitch quickly drops from this attack point down to its sustain level. If we want to reverse that, then we can start making some Bjork. The spread knob is going to give you a bit more of a, it's going to give you a wider stereo image by creating a bit of a chorus in the sound. So it's going to slightly detune your pitch. And you probably won't be able to hear that because it's not stereo on your side, but I highly recommend experiencing this either with headphones or with your speakers on, because you can really tell the difference. It creates a much more lush tone when you adjust that spread knob. But essentially what it's doing is it's slightly detuning the right and left channel of your of the audio that's coming out of your operator synthesizer to create that chorusing effect. Transpose, of course, moves the pitch up or down per semitone. So when we click on the global section, we'll be presented with, of course, our algorithms at the top. But here is, it's called the matrix. And basically the matrix allows us to connect our MIDI controllers to any one of these parameters. So if I wanted to adjust, if I wanted to have, let's say, the velocity at which I hit my key or my drum pad affect one of these parameters, such as the filter frequency or the filter cutoff, I can do that by selecting the parameter, and then I can choose how much it's going to have an impact. So of course, the harder I hit the key, the wider the frequency cutoff or the filter frequency, the higher the filter frequency is going to be affected. That didn't make any sense, but I'm sure you get what I'm saying. So each one of these parameters, velocity, key, aftertouch, pitch bend, and mod wheel, can be connected to two other destinations, connection A and connection B, and then each of the amounts can be adjusted depending on your taste. So not every keyboard has aftertouch control, and I think a lot of people don't really know what aftertouch is, because it's kind of rare, and aftertouch keyboards can be fairly expensive. But you're seeing it pop up, you know, more and more, and it's a really interesting feature. But essentially, what aftertouch is after you've pressed a key or button down, if you're holding that key, how hard you're pressing the key is going to be a parameter that you can then map to some other characteristic or variable. So if you press a key down and then press it harder, you might have it attached to some sort of a filter cutoff. So the harder you press it, the higher or more open the filter becomes to create more of a breathy sound. And it's just really good for maybe creating vibrato or just some sort of performance effect that adds a little bit more depth to your synthesizer. So that is the matrix. Oh yes, of course, you can adjust how many voices can be performed at once. So 6 is the maximum number of notes that I can play at once. If I hit 1, then it will be monophonic. So I'll only be able to hit one note at a time. This is really good for if I want to adjust glide settings. So if I want the note to move slowly from one note to the other, I can do that. Yeah, I think I can do that. Oh, maybe not. Okay. Well, we're getting close to the end, so I'm just going to demonstrate creating probably one of my favorite synthesizer tones using the operator. So first thing I'm going to do, I'm going to have the oscillator A turned on to, let's say, a saw wave. I'm going to have my algorithm as the last one, where all oscillators are playing at the same time. I'm going to choose my second oscillator, and I'm going to choose white noise. I'm going to turn that up slightly. So let's create a new instance of operator. Operator, where are you? Oh yeah, instruments, operator. Okay. Second oscillator, white noise. First oscillator, let's go with saw wave. Now I'm going to add an audio effect of chorus. Going to add a little bit of low frequency modulation, but I'm going to attach it to the filter. All right. Great. Well, I hope that whoever is watching got some good information from that. I'm really hoping that these weekly lessons are going to turn into a bit of a thing. All of my pro members, any of my students that are part of my online lessons for Ableton Live, are able to access these videos in the archive at any time. And then, of course, anyone who is interested in these live streaming live lessons are able to purchase a membership off my website for varying amounts, depending on the length of time that they would like to have the membership. If you have any suggestions, or you'd like to leave me a review, I would really appreciate it if you would click on the link just below the video window and fill out the survey that I've put together. And I would, yeah, thanks for attending, and I hope that you'll attend some more in the future. So have a good night. Peace.